Agora vamos inaugurar e daí a gente já começa aqui na apresentação. Solo si me está escuchando en audio y se bom dia, pessoal. Quero começar primeiro agradecendo a presença de vocês nesse o terceiro dia do evento, como parte do 10º Simpósio Brasileiro Latino-Americano de Internet das Coisas, e também dar as boas-vindas a este evento que está sendo organizado pelo Centro de Transição de Estudos Energéticos Paulista do CPT, que está sendo levado aqui na UNICAMP. Hoje vamos a cumprir com uma sessão 9, que é referente a um tema da atualidade, que é Network and Protocol, e dando início com as apresentações para este dia. Vamos começar com a apresentação de Zero Day Device Identification for IoT Security through Incremental Learning and Adaptation, que vai ser realizada por Ogobuchi e Daniel. Por favor, por parecer, e só lembrando que a apresentação tem uma duração de 15 minutos, e dá 5 minutos de perguntas, e pode ser realizada se desejar.
Okay. We have here present education.
Good morning.
Good morning.
My name is Ogobuchi Daniel. PhD student at UNICAMP Cybersecurity, and then I'm here presenting a paper in English. The paper Zero Day Device Identification for IoT Security through Optimized Incremental and Built Adaptation was authored by my supervisor, professor, as well as my professor in Canada. I did my internship with the Canadian Institute for Cybersecurity in Brunswick. Okay, let's. So, this work has 3 main goals to achieve. Number 3, device identification. We know that IoT network is getting so intense, so dense. We have lots of devices connected together. Then IoT device identification transforms the IoT security from being passive to automated procedure. In the sense that we want to know in our connected network, what are the devices that are speaking at a particular time, what is the information they are sharing, what is the nature of that information that they are sharing, to ensure that our communication system is as secure as possible. Over the period of presentations here, we're talking about how we can make the IoT devices to be usable very, very fast, and then to apply it in a real-world scale. But then, if they are not secure, we may get interrupted in the process of transmission of information. But then, if we do not know the devices that are connected to our network, it becomes another problem. Although we can identify them with their IP address, we can use their MAC address to identify them. But these are also spoofed, they can be impersonated. So we try to look at possible means that are not intrusive, whereby we can identify our connected IoT devices in our network. Again, what do we do in a scenario whereby our models or our algorithms learn about the properties of these devices that are connected to the network, and at a certain time, they may forget or they may require us to retrain those models. how do we make sure that our models are able to retain the knowledge they have? So that's what we talk about incremental learning. In other aspect of it, there could be some changes in the data that the model has learned from, but then we need to make sure that our models as well is able to adapt to this scenario, which is what we call the drift adaptations. Now, in the network of an IoT, we have different kinds of devices ranging from automation sensors, we have our wearable devices. In our hospitals, we have our consumer IoT devices. Now, the heterogeneity of these devices make them very difficult to secure. And also, the resource constrained nature of the IoT devices makes it also difficult for us to be able to implement a high security measure on them. As such, we need a lightweight model, not only lightweight, but also a model that has high prediction capability. So the IoT network is expanding every day with new devices, new protocols, new authentication mechanisms being introduced on the network. How do we ensure that we are able to meet these special needs of the network? Now, one particular thing that we can see is that if we have cameras installed in this auditorium, we have our wearable devices, then when we enter, it gets connected to the network and some also disconnect. In this scenario, we have a model that is already trained to be able to process the data from all the devices connected to this particular network. But if these devices disconnect from the network, what happens to the knowledge that this model has been able to lay about those devices? And if there is a new device that is a new device here that just joined the network, which the algorithm or the model that we have already trained and implemented on our network has no knowledge of the fingerprints or the attributes of this device. It just joined. So this introduces an attack surface that if an attacker is able to get a knowledge of the device that just joined the network, which the model cannot secure, he can use that as an intrusion means to enter the network and penetrate other devices. So the major problem that we're trying to solve is the device identification. We want to make sure that we authenticate every device that is on our network, and then to know if all of them are all legitimate in their communication. And then the device attributes are not static. They change with time. And as they're changing with time, our model needs to be adaptive so that when the attributes of a particular device changes, the model also adapts to that scenario. But if that happens, we may need to retrain the model to be able to adapt to the new changes. And when we have to retrain the model, in the process of retraining and deploying again, we incur costs. Not only do we incur costs, at that span of time that we have to take down the model and retrain, or wait to retrain and deploy, an attacker may invade our network. So we are looking for a possible names in the literature. These are the possible solutions that is in existence. We have to do a continuous training. But if continuous training is done, that is, as the data is streaming over the network, the model is retrained. If the continuous training is done, what about if there is a deviation or a drift in the data? Will the models also adapt? So we have three solutions or three main contributions from this work. One is that we integrate an adaptive sliding window mechanism that is able to detect the drift in the model and also adapt to the drift that it has detected. And then another contribution is that we address a zero-day scenario, whereby if there is a device that joins the network and the model has no knowledge of the attributes of that device, it automatically retrains on that new knowledge it obtains and then be able to identify that device without losing the knowledge on the previous devices that have been learned. And then we update in a streaming fashion. That is, as the data passes through the network, it already does the automated process. So we have, in our methodology, we have a device fingerprinting, whereby we extract distinct information about each of the devices. We do this by using the network packets that they are communicating. Now, I mentioned that using their MAC addresses or their IP addresses can be spoofed or impersonated. So when we use packets or their communication patterns to train the model, it makes it easier for us to be able to know through the behavior of that device or that network. For example, there are devices that send signals in 1 millisecond interval. So if that is a specific attribute of that device, then the model takes note that once we see that this pattern of communication comes from here, this should be able to, this could be this particular device. So the second thing we did was we applied hyperparameter tuning using an feature selection, using the bacterial foraging optimization algorithm, which basically adapts to the behavior of bacteria, E. coli bacteria in the human body when they are searching for food. Then we train our model. The fourth phase, we have to do drift detection, that is to identify if there is data changes or there is model changes in our algorithm or in our data. And when there is a drift that is detected, an incremental learning phase is launched, after which device identification phase comes in. So in our data for the training process, we use 3 different data sets, spanning 4 different data sets, spanning across 4 different periods, and then having different number of attacks and benign samples as well as number of devices. So this is to enable us have a clearer view of what our model can do, whether it's be able to adapt to diverse IoT scenarios. In the feature selection and the feature extraction phase, what we did was that we connected the network packets in the UNICAMP format, that is, as they are communicated from each of these devices. Then we extract the distinct features or distinct attributes like the time, the protocols, and all other features. And then we also perform some statistical analysis on the communication pattern to extract the features that we use in training the models. Then, like I mentioned, we use the bacterial foraging algorithm to select the most feasible or the most salient features from all the extracted fingerprints of the devices, which are then used as our training in our training algorithm to train the model. Now, in the training phase, we are looking at the drift detection. The drift concept is, like I mentioned, when there is a change in the model behavior or in the data that was used to train the model. Definitely, if there is, the model behavior will also change, because at that point, it's not able, it's like a new information is given to that model to analyze. So in this particular case, we use a 2-window system where we set the minimum and the maximum of the windows, that when there is a change in the statistical nature of the training data reaching such a minimum, then we are expecting that there is a deviation in the training data that we have used. So the model will automatically initiate the retraining process. So in the proposed algorithm, we have some other existing method of detecting drift, and we also compare our work with. For example, we have the adaptive random forest with the adaptive random forest algorithm with the adaptive window method of detection. So this work actually uses the river package, of which helps to perform incremental learning or continuous learning process. So these algorithms we are used to compare with what we propose. And then from this result, we could see that at that point, a drift occurred in the training data. While in the process of training, we have to pass the data one after the other, instead of putting all the training data in a bowl. So write the training data in a bowl to the model. So the data is batched in an instance at at an interval, the model does the training and then a prediction on that data. So we compare our model with other existing method of detecting drift and also identifying unknown devices or unknown networks. And our own starts out with better accuracy. Again, we also did the same thing with another data set that we use to train our model, and then our model method also stands out. In terms of the accuracy, the training time, the CPU usage, we have a baseline, which is a normal XGBoost algorithm that we also evaluated. In the normal process, we have the time taken to train the model on the data is about 136 seconds. Then the proposed model took a longer time to train with 216.19 seconds because the data is not provided to the algorithm at once. It comes at an instance. For example, we have 30 rows of data in our CSV file. Instead of pushing the data across the model to learn, it learns one instance at a time. Okay, and as such, it takes longer time to train. However, if you compare it to other baselines, other existing methods of detecting drift in the streaming data, our own model has less train time compared to others. It uses less memory compared to others, as well as uses less CPU. Now, this makes our model resource compatible with IoT devices. In terms of the accuracy and the recall, we can see there is a consistency because the data we use to train the model is balanced. So there is a consistency in the performance across the accuracy, the recall, and others. Now, we measure the rolling accuracy, which is mostly applied to a streaming data or an incremental learning platform or an incremental learning process, where the accuracy is aggregated on average at the interval of the communication. And our model also has better performance compared to other baselines. We did the same analysis on the UNSW 2019 data set. The 4 data sets that we used, we evaluated the model on 4 of them to ensure that what we did actually meets the criteria that we're looking for. Now, in other steps, we also compare the CPU usage for each of these models and the train time. Like I mentioned earlier, you can see from here, we have the proposed model having low time compared to existing method of detecting drift, and then it uses less CPU. And as such, we can say that this model can be deployed on an edge device for zero device detection. This part is the most interesting part of the work. So this actually is the most interesting part of the work, where what we did was that normally in an algorithm, if you train a machine learning algorithm and then you have new data, you need to retrain it. But in this process, we used an adaptive means whereby in the training process, we have to remove one device at a particular time, okay, from our training data and reintroduce the device in the test data. So this is to ensure that the model did not see anything about that device at all in the training data, but the data, the device only appears in the test data to see if it can actually identify that particular device. So in each of the cases, we removed one device at a time, and the model was actually able to identify because of the streaming nature of the data. And secondly, some of these devices have similar attributes. Okay, because of the similarity in the attributes, it is able to know that this actually is a device that is speaking at this point. Now, in a conclusion, we developed and validated and optimized zero device identification model to be able to know which device is connected to our network at a particular time, what the device is communicating, and we'll be able to say, okay, if there is an impersonation of any of the devices, we can detect it. And then in the future, we hope to puts this in a real-time deployment environment for an edge computation optimization, and then introduce an adaptation protocol for other protocols and device types to validate the proposed method. We train them on these different data sets, but we hope that if we can merge all the data sets together, we have a larger number of IoT devices, so that we will be very much sure that this model can adapt to any kind of IoT environment. But the interesting thing is that it not only identifies where there is a drift in the data that was used to train a model, it also detects when there is a new device that is introduced on the network. These are our contribution to this one. So in this, I want to say thank you, and I want to thank FEEC, the Canadian Institute for Cybersecurity, FAPESI, and CAT for the support on this project. Thank you so much.
Obrigado pela apresentação para eles também. Agora vamos passar para a sessão das perguntas. Se alguém na plateia tem alguma pergunta, por favor, para o apresentador.
Hello, good morning. First, I want to congratulate you for your work, because I can see it has a lot of contribution, sorry. And after that, I saw your proposal come with that kind of retraining of the model, right? So what I didn't see there, and I would like to know is, if you want to come, like not the environment that change the device every time. So in which time you plan to make the training?
Okay, thank you so much for the question. The retraining occurs when there is a drift. Now, the adaptive sliding window mechanism, drift detection mechanism that is introduced in the modeling and training process, actually detects that there is a change in the data that is used to train the model. So once it detects that there is a change within the specified limits that we introduce, okay, there is a statistical change in the data that was used to train the model. The retraining process is initiated, and the model has to go through that process again. So if we have that model deployed on a network, we want to monitor a particular setup, and then we bring a new device. That device sends signal on that network. The packets that goes to that device already tell the model that there's something that has changed in the training network, because we collect that packet and then extract the features, feed it into the model, and at that moment, it notifies the model that it's a change, and then the training process is initiated.
Okay. Then what time takes your model to be retrained?
Like I mentioned, yeah, the time that we mentioned there was 218 seconds for the model to train on the entire data. Okay, as the data is trained from the first part of the data in the database to the end is 218. So if you want to know what it takes to train on a single instance of data, we just need to do the calculation of the total number of instances that we have divided by the number of time. So which will not measure at this time. Okay?
Thanks. Thank
Thank you for your answer, and again, we will learn for the presentation. Thank you much. Vamos continuando com as seguintes apresentações. Vamos a continuar com o trabalho intitulado LoRa Radio Link Quality Assessment Strategy Using Sensitive as a Link Quality Indicator, que vai ser apresentado por Pedro, Henrique e Bertoleti, parte da técnica UNICAMP. Por favor, confirme se consegue escutar a gente e se consegue, por favor, compartilhar a tela para iniciar a sua apresentação.
Sim, eu escuto vocês. Vou compartilhar a tela agora.
Obrigado.
Por favor, me confirme se a tela está ok.
Sim, tá aparecendo para a gente aí. Pode começar com a sua apresentação. Obrigado.
Vou começar agora, obrigado. Hi there, my name is Pedro Bertoleti, and today I'm going to the LoRa radio link quality assessment strategy using sensitivity as a link quality indicator. Let's start with motivation. Why reconsider LoRa link quality evaluation? Well, traditionally, link quality evaluation, often said or provided by manufacturers, relies only on RSSI, which means received signal strength indicator. So it relies only on received or RX power, and this is not complete, as it will be presented from this point on this presentation. RSSI alone does not represent communication efficiency, as it only stands for the received power or received transmission power. So this is not enough to assess the LoRa link quality evaluation. This approach ignores packet loss and data rate effect on link quality evaluation. So IoT solutions that require more complete metrics to ensure reliable connectivity suffers from lack of link quality evaluation using this approach. So put everything together is the motivation to reconsider LoRa link quality evaluation, which consists of a new or reviewed or revisited strategy to evaluate the LoRa link quality as we present here. So first of all, to better understand what comes next in this article, let's see what is sensitivity, okay? The concept of sensitivity relies on three information piece, which stands for RSSI, which means the power, the received power, the data rate from the wireless communication, and also the PER, which stands for packet error rate, which means how many percent or how many packets are lost from a transceiver to a receptor in the wireless communication. So usually, and not completely formed, sensitivity is as we talked later, is how can I say, is said as equal as RSSI. In this work, sensitivity is referred as is full, which means the combination of RSSI, PSR, which means packet success rate, which is the complement of the PER. So PSR and PER sum are equals 100%, and data rate or effective throughput, in order to make it possible to assess LoRa link from both effectiveness and efficiency perspectives. As a basis of every measurement and test make so far on this article, we authors use TPM and MOT framework as a solid basis. The TPM, which stands for three-phased methodology, means a methodology developed for the members of WISTEC and at FEEC here in UNICAMP, aims to architecture any IoT solutions into 6 abstraction levels, as you can see at the right of the screen. And all of these levels are defined along 3 phases. Phase 1, business phase, where the business people tell what is needed to monitor, like temperature, air humidity, and so on. Phase 2, where the requirements are written, and the phase 3, where implementation is effectively done. And communication between the level 1 and level 2 is handled by MOP, or Management Over Tunneling Protocol, which is agnostic to the radio technology used as communication link. The MOT, or MOT, it comprised by headers, which include RSSI and packet counter, payload, useful data, and also the metrics to enable wireless network management, including the PSR and PER. Well, this article uses, as said before, DPM and its framework, including MOT, as a solid base to achieve both hardware and software metrics needed to infer LoRa sensitivity in real-world scenarios. Oh, let's go forward to the experimental setup. The location of all tests is here at UNICAMP, at FEEC, which is the Department of Electrical Engineering in Computer Engineering, using indoor points, actually 1 indoor point and 3 outdoor points, as we can see at right in the figure right side of the screen. Okay, so point 1 is indoor, 2, 3, 4 are outdoor. In each test point, 2,500 measurements of RSSI, PSR are done, and this is done at 2 fixed data rates, as you can see down below here, 3.8 kbps, and for a high rate, 21.8 kbps. And also, 2 different LoRa radios have been used in these tests. The first one, eByte A2-D16-M, and NiceRF LoRa 1276. So, to sum up, we have 2 LoRa radios, and for each point, we have 2.5K measurements of RSSI, PSR, and 2 different data rates, which will compose a data set, as we will see later on this presentation, that sum up the results. The experimental assembly is composed by a sensor node and a base radio, both using microcontrollers to handle all the communication and MOT protocol. Each test point is a device composed by a microcontroller, a LoRa radio, which can be one of 2 options, as said here. So for each test, for each radio, all the tests are done, and a power bank to power it without depending or relying on a AC power source. The base radio is kept in a fixed position in WSTEC lab, so it does not move, and the sensor node moves around the points 1, 2, 3, and 4, and to implement the other phases or other levels of the 3-phase methodology, which means level 3, 4, 5, and 6, a Python script are using in a computer that's located at WSTEC lab. Also, it does not move. It's kept in a fixed position as base radio. As the results, considering the first LoRa radio, which is the eByte A2-D16-M, show that at point 1, we got the strongest RSSI testing point, having minus 61.3 dBm, and also at a lower data rate and almost 99.6 PSR. And point 3, which is an outdoor point, we got the weakest RSSI test point, having minus 92.0 dBm and a higher rate, lower rate too, and 99.7 PSR. Considering these results and also the other results shown in table 2 at the right side, we came to the conclusion that higher SSI does not mean better link quality. As we can see here, the PSR for the minus 92.0 dBm at 0.3 is higher PSR, which means less packets has been lost, as considering the 0.1 that got the strongest received power. So higher SSI does not mean better link quality, which means that access a LoRa link quality radio for its SSI, it's not enough. And in a general way, lower data rates implies in better performance. So the lower is the data rate, the better is the PSR. So it also confirms that in wireless link communications, when you are who have struggles to transfer data from one point to another, a possible solution is to decrease the data rate. For the second LoRa radio, we came to the following conclusions. Point one, as happens in another radio, is the strongest RSSI test point, and point three is the weakest RSSI testing point. And also we have here anomaly, which means the unexpected lower PSR at lower data rate has been observed in this test. This anomaly can be explained by the unpredictability inherent to every radio link, which means moving obstacles and interferences, as the ambience between the transfer and reception parts of this link radio, it's moving, it's dynamic. So at the time these tests have been achieved, something has changed in the ambience and impact on these metrics. So anything between the transmitter and receiver influence the results. This anomaly is actually a very interesting point of any wireless link communication, which means unpredictable things can happen, and some points are out of range. Okay, which means that point number 4, as happens in the previous tests. And the additional conclusions, as seen in the previous radio, higher SSI does not mean better link quality. Coming to the end of the presentation, you get the discussion and conclusion section, which means RSSI alone is not sufficient to assess link quality. As tests have shown, higher SSI does not mean better link quality. Sensitivity is composed by 3 items, 3 measurements, which means RSSI, data rate, and PSR. And this composes a complete LoRa link assessment. Once it combines effectiveness, which means the RSSI measurement, and also efficiency, which comprises the PSR part of the sensitivity. And also, from the test, we can see that achieving 100% of PSR is rare, it's not common. And also, considering that it's very uncommon or very unusual getting 100% PSR, it means the retransmission mechanisms are essential in IoT. Once tests have proven that packet losses are very common through any wireless communication. Here we tested LoRa, but this is valid for Wi-Fi, Bluetooth, anything that comprises wireless communication. Therefore, protocols like MOT or MOT here are required to ensure reliable IoT solutions from both usage and network management perspectives. And we came to the end of the presentation. I hope this is good for you. This is useful for you. And now I'm open to questions if you have. Am I still online, right?
Se alguém dentro da plateia quer fazer uma pergunta, por favor, fique à vontade.
Bom dia. Parabéns pela apresentação. Muito interessante o trabalho.
Yo decidí saber ahí por qué no experimento vocês colocaram aí 2, 3, 4 tão perto, né? Porque o LoRa ele tem coverage range de quilômetros. Eles poderiam estar mais distantes. Não sei se você poderia explicar, talvez, qual foi a finalidade de que eles estejam aí tão perto dessas posições do LoRa.
Desculpe, o áudio está um pouco empolgado. Você perguntou por que no pontos 3 e 4 não pegam?
Isso. Os pontos 2, 3, 4 estão perto entre eles, né? Porque todavía para estar más afastado aí por as características técnicas mesmo do LoRa.
Ok. O ponto 4, em termos de distância, ele é o menor possível, é o maior possível, perdão, em relação ao ponto de medição de rádio base, né? Porém, isso serviu para mostrar, né, uma razão que explica que a visada, o caminho de comunicação entre os pontos nem sempre é o que a gente olha ali. Então, o ambiente em si influencia na comunicação. Então, entre o ponto 3 e 4, havia movimentação de pessoas, mais obstáculos, vegetação, o caminho tinha uma distância maior, então isso mostra que pontos mesmo próximos, né, como o 3 e o 4, podem apresentar uma diferença tal que inviabiliza a comunicação. Então, o link de rádio, mesmo o LoRa sendo um link long range, né, como o próprio nome sugere, os obstáculos, os ofensores de comunicação podem sim ser fatais ali para a comunicação. O ponto 3 já teve uma comunicação bem deteriorada, então estava no limite da recepção. Então, do ponto 3 para o ponto 4, qualquer coisa poderia afetar, e foi o que aconteceu. Como tinha circulação de pessoas, maquinário e tudo mais, mesmo sendo outdoor ali, né, nas proximidades, isso acabou deteriorando o sinal ao ponto dele não conseguir ser recebido. Então, isso mostra uma característica de links de rádio, onde nem sempre lugares próximos, né, vai haver a comunicação, às vezes qualquer coisinha vai fazer cair. Ficou claro?
Sim, ficou claro. Só mais uma pergunta. O RSSI, na métrica que vocês estavam estudando ali, do RSSI, vocês chegaram na conclusão aí que não dá para usar essa métrica para avaliar a qualidade, né, da conectividade. Mas daria para usar essa métrica para estimar, por exemplo, um obstáculo assim, por exemplo, as condições climáticas ou outro tipo de obstáculo como as pessoas, assim, do entorno mesmo da comunicação? Vocês, não sei se chegaram a ver algum padrão aí nessa métrica.
Entendi. Existe um trabalho prévio de outro autor, né, em outro congresso, que ele conseguiu comprovar uma relação entre o RSSI e a movimentação de pessoas numa fábrica, incluindo um monitoramento constante ali ao longo período, né, mais de 24 horas. Ele conseguiu ver que em horas de parada, hora da noite, do almoço e coisas assim, o RSSI se comportava com um desvio padrão menor, então ele ficava mais estável. Então, é possível, com o RSSI, prever algumas características do ambiente, como movimentação de pessoas, mais ou menos ofensores. Porém, o RSSI sozinho, ele não é suficiente para dar uma qualidade, um link de qualidade de rádio para LoRa, né? Qualquer outro rádio, porque ele considera somente a potência de recepção e não o quão eficiente foi. Fazendo um comparativo, né, dessa linha do artigo, é como se fosse assim: se você tivesse próximo a uma pessoa que fala um idioma que você não conhece, você até ouve o que ela fala, mas você não entende. Então, então isso significa o seguinte: a potência de recepção que você ouviu, né, o volume, foi bom, mas você não entendeu o que estava ali por causa de um ofensor que foi a língua, algo do tipo. Isso é a mesma coisa com conexão sem fio, comunicação sem fio. Às vezes você tem uma potência de recepção, só que o sinal é tão degradado ou está de uma forma tão inesperada que você não consegue entender. Por isso que é importante considerar o PSR, que é aquela métrica, né, ou o PER, que é o seu complemento, de forma que você consiga medir tanto se recebeu com uma potência boa e o quão efetivamente foi compreendido do receptor. Então, e junto também com o item da data rate, né, que é a taxa de dados, que a gente viu que influencia. Então, esses 3 itens juntos formam uma métrica de maior qualidade do que simplesmente o RSSI, entendeu?
Muito obrigado pela resposta, professor, e parabéns de novo pelo trabalho. Agora, dando sequência com as seguintes apresentações, vamos confirmar se tem alguma pessoa para poder fazer a apresentação do trabalho titulado Joao, Informing and Beyond Risk Design for Efficiency Wireless Energy Transfer.
Olá, eu estou online, só que eu tive algum probleminha com o meu note e eu vou ter que fazer a apresentação no notebook de uma aluna aqui, ok?
Do trabalho que você vai fazer a apresentação?
Oi, desculpa?
De qual trabalho que você vai fazer a apresentação?
O trabalho the diagonal is designed for efficient wireless energy transfer. Meu nome é Victoria. Eu só vou compartilhar a tela aqui, só um minutinho.
Fique à vontade para iniciar, só lembrando que tem 15 minutos para a apresentação e, na sequência, máximo 5 minutos para perguntas. Pode realizar em português e em inglês.
Ok, um minutinho apenas. Vocês estão vendo a minha tela? Olá.
Pode começar.
Okay, so my name is Victoria Souto, and I will present the paper entitled Informing the Beyond Diagonal His Design for Efficient Wireless Energy Transfer. This paper was developed by me and some research from the University of Joao, the Federal University of Santa Catarina, and Aeronautics Institute of Technology. So the presentation will be divided in 5 points. So first I will give an introduction of the main goal of the paper, the system model and optimization problem. And so I will finish the presentation with the simulated results and the conclusions. So the main idea of this work is to investigate the performance of wireless energy transfer system assisted by beyond diagonal HIS. So we propose a solution based on particle swarm optimization to maximize the energy harvested by IoT device, considering some constraints of the beamform at the power beacon and also the constraints of the beyond diagonal HIS architectures. In this case, we evaluate different architectures of beyond diagonal HIS, such as the single connected, that is the classical RIS, and the fully connected and group connected architecture. So here we have the system model evaluated in this work, where we consider a power beacon equipped with multiple antennas. And here we also consider analog beamforming because of the this architecture of beamforming is simple and has a low consumption of energy. So we consider the beyond diagonal HIS assisting the communication between the power beacon and the IoT device. And here we have the channel, the matrix channel between the power beacon and beyond diagonal HIS, the vectors channel between the beyond diagonal HIS and the IoT device, and also the vector channel between the power beacon and the IoT device. So from this system model, we can define the power harvested by the IoT device from this equation, where we have two new variables. The phi is the phase and amplitude of the beyond diagonal his, and W is the beamform at the power beacon. After that, from a nonlinear model, we can have the energy harvested by the IoT device. Here in this equation, we have the energy harvested by the IoT device, where TC is here we consider that TC is the time that the power beacon is pointed to the IoT device, and we also consider that this time is the same that the coherence time of the channel. And the other variables are defined based on the power harvested by the IoT device and the circuit's configurations. In this paper, we consider the beyond diagonal RIS, as I said. So this new type of RIS has three common architectures. The first one is the single connected, which is the classical RIS, where each element is independent. So we can see that they don't have connections between each other. After that, we have the fully connected and group connected. The fully connected is the second figure, where we can see that all elements are connected to each other. And the group connected, we have groups. The groups are independent, and the elements into these groups are connected to each other. So from these architectures, we have some constraints. For example, for the classical beyond diagonal RIS, we have a diagonal matrix, and for the fully connected, we have a non-diagonal matrix, but we have to guarantee that the matrix is orthogonal and symmetric. And for the group connected, we have a block diagonal matrix, and we have to guarantee that each block has a matrix that is orthogonal and symmetric. So the main objective of this paper is to maximize the energy harvested by the IoT devices by jointly optimize the beamform vector at the power beacon, which we denote as W, and the reflection coefficient matrix at the beyond diagonal RIS. In this problem, we have to satisfy some requirements, such as the analog beamforming, which is the first constraint, and also the constraints of the beyond diagonal RIS, such as the orthogonality and symmetry of the matrix. If we analyze this problem, we can see that based on the constraint, this problem is non-convex. So classical math methods cannot solve this problem. To solve this, we propose a method based on particle swarm optimization, which is an heuristic technique that is fully applied in this type of problem. And here we have the main steps of the particle swarm optimization. So in the first step, we'll randomly generate the first population. In this case, the first population, or each particle of our method, is one vector of the beamform and one matrix for the beyond diagonal RIS. So here we will generate a population that is a swarm composed of n particles. So after that, we will evaluate each particle, that is each pair of beamform and matrix based on the energy given in this equation. So we will compute the fitness of each particle based on the energy harvested. After that, we will update the two parameters that we call G-best and P-best. The G-best represents the swarm experience, and the P-best, the P-best represents the individual experience. It's changed here. And the G-best is the swarm experience. That is, for example, the G-best is the best pair of beamform and metrics, the beyond diagonal metrics that achieve the best solution, the best fitness until now. And the P-best, it's the individual experience. So what is the best part that each particle has experienced? So after that, we will update the velocity and position of each particle. So the velocity is given by equation 4 and the position is given by equation 5. So after that, we will generate the new swarm. This new swarm is based on the positions computed by equation 5. And so we will check if the stop criterion is met. So if not, we will return to step 2. If we finish it, otherwise we will finish our algorithm. Here we have a more simple representation of the solution. So we will randomly generate L particles, where each particle is based on the beamform and the phase. After that, we will compute the fitness. So we'll find the G-best and P-best based on the fitness. This is for the first population because in the first we have to randomly generate the particles. So after that, we will run the algorithm for any IT iteration. So we'll compute the omega, which is the inertia factor. It's like a parameter that will define the velocity of each particle. So after that, for each particle, we will update the beamform, the beyond diagonal, his metrics. We will apply the KR decomposition to guarantee the orthogonal and also will guarantee the symmetry of the metrics. So we'll guarantee the constant modulus of the beamform to guarantee the constraints of the analog beamform. We will compute the fitness for the new part of beamform and beyond diagonal metrics, and we will update the P-best and G-best. So if you reach the maximum number of iterations, we will return the G-best. So the proposed solution was evaluated considering the single group and fully connected architecture. Here we refer as classical HIS when we are talking about the single connected beyond diagonal HIS, and also we consider as benchmark the scenario without HIS, where the beamform at the power beacon is designed considering the optimal solution. So here we have the simulation parameters, the number of elements of the beyond diagonal HIS, the number of antennas at the power beacon, and the coherence time of the channel, the frequency, and other parameters that we consider in our simulations. So we have some results. Here we analyze the harvested energy considering a variation of the number of elements at the beyond diagonal HIS. Here we can see that even considering the classical HIS, we can improve considerably the energy harvesting when compared to the benchmark without HIS. And we also verify that even consider architecture that is simple, for example, the group connected with 5 groups, we can achieve a close to optimal performance. In this case, in the fully connected, we consider that all the elements are connected to each other. So the complexity, the computational complexity to compute all these elements, all the elements of the matrix is very high. So when we have a matrix with a high number of elements, this can become prohibitive. So here we can show that we can achieve a close to optimal solutions even with only 5 groups. Here we can also evaluate the energy harvested by the IoT device, considering different numbers of antennas at the power beacon. Here we can also show that considering the assistance of reconfigurable intelligent surface, it's fundamental to the wireless energy transfer, and we also can show that even considering a small number of groups, that is considering a simple architecture of beyond diagonal his, we can achieve a close to optimal performance. And here we have a variation of the Rayson factor. And here we can show that our proposed solution, it has, how they say, a constant performance for different risk factor. Here consider the direct link. We demonstrate that our solution is robust for different types of channels. And here we can see the convergence of the proposed solution, and also we can see that even when we increase the number of elements at the beyond diagonal his, the number of iterations that we need to, that our proposed solution needs to converge, is still very close to each other, which is important when we consider a large beyond the diagonal his. So, as conclusion, in this work, we propose a PSO-based approach to maximize the energy harvesting in the wireless energy transfer system. So here we consider the project of the beamform at the power beacon, and also the project of the reflection matrix at the beyond diagonal his, considering different architecture, for example, single, fully, and group connected, and also we consider as benchmark the scenario without the his. And our results demonstrate that the fully connected beyond diagonal his increase the harvest energy by at least 35%, and the group connected architecture, even when we are consider a simple architecture. So we also could verify that if with a limited number of his elements, the group connected beyond diagonals, his yields an energy increase of at least 80% of over the scenario without his, which is a very impressive results. And also the results demonstrate that beyond diagonal his integration significantly enhances the energy harvesting, even with low complexity group connected designs. And as future works, we intend to study the multi-user scenario, and also we intend to study different architectures for the beyond diagonal his, because here we have the common ones, for example, single, fully, and group connected are the most popular in the literature, but they have some limitations. For example, the full, the problem is the complexity, and the group connected, it's fixed, so we cannot dynamically configure these beyond diagonal his. And there are some studies that show that we can define the architecture of the beyond diagonal his in real time. So we are investigating different groups consider dynamic beyond diagonal his, and also consider static beyond diagonal his to try to compare the performance in the wireless energy transfer systems. So I'd like to thank you your attention, and if you have questions, please feel free.
Muito obrigado pela sua apresentação, Natália. E, bom, se não tivermos uma pergunta da plateia, tenho entendido que você vai continuar a seguinte apresentação, né? Também.
Não, eu vou passar. A Natália vai fazer a apresentação seguinte. Eu tive que correr para o notebook dela.
Tá. Então, a seguinte apresentação
Só um momento.
Então, a seguinte apresentação que vai ser o Optimization of the Number of device assisted by RF device with. Bom dia, é Natália, que vai apresentar também.
Bom dia.
Bom dia, estamos ouvindo bem?
Sim.
Tá, então fique à vontade para poder começar. Tem tempo limite de 15 minutos para apresentar, seguido de 5 minutos máximos para perguntas. A apresentação pode ser em português ou em inglês. Pode começar, fique à vontade.
Vocês conseguem ver minha tela?
Não, vendo sim.
So, good morning. My name is Natalia Batista from the National Institute of Telecommunications, and today I'll be presenting this work titled Optimization of the Number of IoT Devices Assisted by RF-Based WET Systems. This is a brief overview of my presentation today. First, I'll give an introduction and describe the system model considered. Then, I'll present the optimization problem and proposed solution, followed by the numerical results. Finally, I'll conclude the presentation and address any questions you may have. The significant expansion of IoT solutions has intensified the need for sustainable energy resources, since batteries or cables have high costs and high maintenance requirements. In this context, WET systems based on RF signals have emerged as an alternative approach. It uses power beacons equipped with multiple antennas to direct the energy beam toward the IoT devices. The main challenges involving WET systems are channel state information acquisition and limited power beacon range. So, to address these challenges, this work aims to jointly optimize analog beamforming and power beacon placement to optimize the number of IoT devices powered in the system. Our main contributions are the development of a numerical method that, unlike AI-based approaches, does not require large datasets or high computational costs, and beamforming optimization based on statistical CSI. Additionally, simulation results show an increase in the number of power devices up to 29.1%, with beamforming optimized under perfect CSI and a solution based solely on statistical CSI closely approaches the ideal performance. This model considers P-power beacons, each equipped with N antennas that wirelessly power K IoT devices, each with a single antenna. The RF power received at the kth IoT device when the Pth power beacon directs its beam toward the jth device is given by this equation. And this work assumes that IoT devices can opportunistically harvest energy while neighboring devices are targeted for charging. It also assumes that devices can harvest energy from multiple power beacons. Therefore, this equation describes the total amount of energy harvested by the kth IoT device, considering the beam sharing effect and multiple power beacons. Based on the objectives of this work, the optimization problem aims to maximize the number of IoT devices that satisfy a minimal energy requirement, while jointly optimizing the beamforming configuration at the power beacons and their spatial deployment. The optimal solution to the previous optimization problem requires perfect state information at the power beacons. Therefore, this work adopts a suboptimal approach based solely on the statistical CSI knowledge
and the resulting suboptimal beamforming vector is constructed using equal gain combining and is defined by this equation. By substituting this result in the original optimization problem and by incorporating the nonlinear characteristic of energy harvesting through a minimum received power constraint, the optimization can be reformulated as maximizing the number of devices that meet a minimum received power constraint while respecting the system's limited area. The last optimization problem is still nonlinear. Consequently, finding a global optimum with conventional methods is still challenging. To address this problem, we adopt the quasi-Newton approach, which avoids the high computational cost of the exact Hessian matrix. Specifically, we employ the symmetric rank 1 variant, which preserves the curvature properties of the objective function. This method iteratively updates a Hessian approximation and ensures a reliable search direction using gradient information. Based on the proposed optimization problem and on the SR1 requirements, the objective function can be expressed as f of I, and this function aims to minimize the number of IoT devices that do not meet the minimum power constraint. Its gradient can be defined by this expression, and the SR1 method uses a truss region strategy to define the Hessian approximation and the step. Therefore, it builds a quadratic model function, m of I, to represent the objective function around the current point. And the step of the algorithm is calculated by minimizing this quadratic model subject to the absolute value of the step being smaller than the truss region radius delta I. After calculating the gradient at the step, the SR1 method updates the Hessian approximation following this formula. The method iteratively computes the gradient, the Hessian, and the step, which can be accepted or rejected for a given number of iterations, or until the error is lower than the stipulated tolerance. Unless otherwise stated, these are the parameters considered in the simulations. We used 70 IoT devices distributed through an area with 200-meter radius, and we also assumed 5 power beacons equipped with 4 antennas each. This first graph shows the number of IoT devices that satisfy the minimum energy constraint as a function of the total number of devices in the system. The proposed method enhances the number of successfully powered devices by up to 29.1% when compared to the random benchmark. This underscores the importance of power beacon placement in dense IoT scenarios. Also, the statistical CSI method approaches the perfect CSI results, highlighting the robustness of the proposed method even when relying only on statistical CSI. This graph shows the effect of increasing the number of power beacon antennas on the number of successfully powered devices. As the number of antennas grows, beam directionality improves, resulting in more effectively charged devices. However, this gain is not linear, since narrower beams reduce the beam sharing effect, potentially increasing charging time. Moreover, a larger number of antennas increases hardware complexity and energy consumption. Despite this, the proposed method achieves near optimal performance and outperforms the random benchmark. Here, we present the influence of the number of power beacons on the system performance. From the graph, we can note that a higher number of power beacons leads to a significant increase in the number of charged devices, demonstrating the importance of employing multiple power beacons in wet systems. Also, the performance using only statistical CSI remains close to perfect CSI, even as the number of power beacons increases, confirming the practicality of the statistical CSI-based approach. Lastly, this work proposed a low-complexity strategy for jointly optimizing power beacon placement and analog beamforming in wet systems, aiming to maximize the number of IoT devices successfully charged. The numerical results show that the proposed method outperforms random power beacon placement, despite relying only on statistical CSI, confirming the method's effectiveness for large-scale, energy-constrained IoT deployments. Thank you very much for your attention. I am available to answer any questions you may have.
Obrigado por essa apresentação, Dani. Agora vamos passar para a sessão de perguntas. Se alguém dentro da sala tiver algum questionamento que você fazer. Pronto. Muito obrigado pela sua apresentação e parabéns pelo trabalho desenvolvido. Muito obrigado, viu?
Obrigada.
Agora, passando para a seguinte sessão, vamos continuar com o trabalho intitulado A Transparent Baseline for LoRa Device Fingerprinting with CMA. Vai ser apresentado pelo Joao Henrique. Júlio. Sim, desculpa. Vamos. Tem que ser os slides. Sim, isso.
Okay, good morning everyone. My name is Júlio Graziano Pontes from Universidade Federal do ABC. I will present a study about a baseline for identifying LoRa devices using convolutional networks. Well, to implement authentication in IoT is a challenge. The traditional methods are efficient, but usually they are too heavy for constrained devices. So, as a result, weaker or incomplete implementations may leave the devices open to attacks such as impersonation or key compromise. This opens the door for other approaches for authentication, such as physical layer with RFFI. Well, radio frequency fingerprinting identify devices based on impairments inherent to the hardware, to the fabrication, to the components, and produced on the digital to analog phase, the front-end radio transmitters. These small analog differences, they are consistent and measurable, so they can be used as like digital fingerprints of the transmitter. The idea here is not to replace traditional methods like cryptography and KPI and other things, but act as additional or fallback layer of security for authentication. Well, the recent studies have considered machine learning, deep learning for RFF, some even exploring different channel conditions, different receivers, and other kind of domain variations, but most of them are made on controlled setups, and the transparency of the experiments are still limited. So it's much difficult to find information to reproduce the studies. So our goal is to provide a clear, documented, and reproducible model for use of everyone to reproduce and compare with future works. So the objective is to implement a very compact CNN that is able to classify a lot of devices by RFF and make available all data, all scripts, all code for future use and comparison. Our contribution is a framework that can be used as a benchmark for future studies, supporting fair comparison and consistent evaluation. The data set. We used a public data set from Shane and others. It contains, we used actually a subset that contains 30 PyCon LoRa devices with the same chipset, exactly the same model. We capture 500 bytes each for each device. Capture from the preamble, the 8 first subchips, so ending on 15,000 IQ captures, which is the raw signal. The pre-processing pipeline, we normalized the signal in terms of power, then converted into spectrograms using the short-time Fourier transform. And then we cropped, there is the spectrogram, so we cropped to the central part of the picture to preserve only the most relevant information. Then we fed it into a CNN. Here we try to use CNN as simple as possible. So we implemented 3 convolutional layers with filters starting from 16, then 32, then 64, followed by a dense layer with 128 neurons, and classification with a softmax for 30 classes. Results. Well, we've got, for this setup, 90% of accuracy, and with a macro F1 score of 0.98, and AUC ROC of 0.999, showing an excellent classification power. So the model converged like smoothly, and with no signs of overfitting. Confusion matrix showed some few confusions in like 3 or 4 devices, showing that it's possible to classify devices using only the radio signals. This network have only 813,000 parameters, so it's far smaller than the comparable networks in literature. We had 11 milliseconds of inference time on GPU and 15 milliseconds on CPU. So it's suitable for real-time applications and for edge devices. What else? Well, we made all the code, scripts, and data reference available for future use and comparison. Conclusions. Well, in summary, this studies builds a transparent and reproducible baseline for device fingerprinting. Our CNN is lightweight and achieves 98% accuracy with low computational costs. Future work includes cross-domain validation, which is getting data from different days, different channel conditions, different receptors. What else? Use of transfer learning for classifying or identifying unseen devices. The idea here is to move from control conditions to real-world conditions. I'd like to thank my co-author, Professor João Kleinschmidt, for his guidance and all the support. Now I'm open for questions.
Primeiro, a apresentação e ela também, o trabalho. Passando para a sessão das perguntas, talvez se alguém começar, fazer alguma pergunta sobre a apresentação. Bom, eu tenho que fazer uma pergunta sobre aí. Ela falando sobre a rede que vocês montaram, talvez que vocês definiram isso como vai estar. Isso poderia ser também utilizado às mesmas medidas para vocês montar famosos acessos, conjuntos, ou se a gente precisa não modificação?
Pode ser usado em qualquer dataset, só mudando a forma de captura, né? Capturando os dados em formato adequado, ele pode classificar outros sobre outros datasets.
Se seriam separados, para esse problema assim.
Sim, inclusive então, toda a rede salva, está disponível os links, todo o código, absolutamente tudo está disponível para reprodutibilidade.
Muito interessante o trabalho. Obrigado bastante. Parabéns pelo trabalho. Bom, continuando com as apresentações e para finalizar essa sessão, temos a apresentação do trabalho intitulado Automated Machine Learning for IoT Security, a Comparative Studio.
Oi. Bom dia, vocês conseguem me ouvir? Oi. Oi.
Oi, bom dia, tudo bem?
Bom dia. Vocês estão conseguindo me ouvir?
Estamos ouvindo sim. Você consegue escutar a gente aqui?
Sim, agora sim.
Tá, perfeito. A gente estava ouvindo sua tela, fique à vontade para finalizar sua apresentação. Tem 15 minutos, a gente quer realizar isso em inglês.
Ok. Vocês estão conseguindo ver minha tela?
Estamos vendo sim.
Ok. Então, bom dia a todos. Meu nome é Rivaldo Marinho, sou aluno do programa de pós-graduação da Universidade do Estado do Amazonas. Vou apresentar meu trabalho desenvolvido em parceria com o professor Tiago, né, que é intitulado Automatic Machine Learning for A2-D16-M, a Comparative Study of Intrusion Detection Approaches. O contexto do nosso estudo, né, ele está dentro do âmbito da internet das coisas, né, que tem transformado diversos setores como saúde, cidades inteligentes e agricultura, ao conectar bilhões de dispositivos à internet. Porém, essa conectividade massiva também aumentou significativamente a vulnerabilidade de segurança. Por exemplo, eu trouxe alguns dados que entre 2018 e 2022 houve um crescimento de 53% nos ataques cibernéticos, com mais de 1,5 bilhão de ataques direcionados a dispositivos IoT. Apenas em 2021, tivemos todo esse aumento, né, de ataques. Logo, as soluções tradicionais de detecção de intrusão exigem, né, profissionais especializados e não são facilmente escaláveis. Diante desse cenário, o aprendizagem de máquina tem se destacado aí, né, mas, no entanto, necessita de profissionais especializados para estar aplicando esse tipo de tecnologia. Logo surge também o aprendizagem automatizado, AutoML, né, como uma alternativa eficiente, pois ele automatiza a escolha de algoritmos e seleção de atributos e o ajuste de hiperparâmetros, reduzindo o tempo de esforço humano. A motivação que se deu a esse trabalho se baseia em 3 pontos principais. Primeiro, o aumento de ataques cibernéticos em redes IoT, que exige métodos rápidos, precisos e autônomos de detecção. 2, os modelos tradicionais demandam muito tempo de configuração e conhecimento especializado, e há poucos estudos que exploram o AutoML aplicado à segurança IoT, especialmente no contexto do protocolo MQTT, que é amplamente usado em aplicações residenciais e industriais. Dessa forma, o nosso objetivo desse trabalho foi comparar diferentes frameworks AutoML para identificar qual deles oferece o melhor desempenho na detecção de tráfego malicioso em redes IoT. O nosso estudo foi estruturado com base em 3 perguntas de pesquisa, né? A primeira, quais frameworks AutoML alcançam o melhor desempenho na detecção de ataques em redes IoT? A segunda pergunta é qual o impacto da automação na precisão, no recall e na estabilidade dos modelos? E a terceira pergunta, qual os modelos AutoML superam os métodos tradicionais reportados na literatura, né? Essas questões, elas orientaram o nosso estudo referente ao planejamento dos experimentos e análise dos resultados. Eu trouxe também aqui a arquitetura proposta e versus a arquitetura tradicional que é empregada já com o uso de modelos de machine learning, né? Então, onde você tem o input dos dados para processamento, a extração de features, a seleção de algoritmos, otimização de hiperparâmetros e avaliação da performance do modelo, onde você precisa treinar um modelo e, dependendo do resultado que você vai ter, você vai reavaliar e fazer ajuste dos hiperparâmetros, e tudo isso de forma manual, né? Então, você precisa ter um conhecimento prévio de ciências de dados, e então isso se torna um pouco complexo, né? Então, a arquitetura que a gente propõe aqui é uma arquitetura automática, né? Onde você tem o input de dados, o pré-processamento, a extração de features, a seleção do algoritmo, a otimização dos hiperparâmetros e a avaliação do modelo, tudo de forma automática, reduzindo o esforço, né, especializado com a aplicação desse pipeline. Falando um pouco agora sobre o dataset, né, que foi utilizado, os experimentos foram realizados utilizando o dataset MQTT7, proposto por Vacari e Joao em 2020, né? Esse conjunto de dados está disponível no Kaggle. Ele simula uma casa inteligente por dispositivos IoT, comunicando-se pelo protocolo MQTT como base, né? Ele é amplamente adotado em sistemas IoT e ele possui um número total de registros de 330.933 registros, né, de conexões de dispositivos comunicando na rede. Sendo metade desse tráfego legítimo e metade tráfego malicioso, né, que são conexões maliciosas. Então, a gente tem um dataset balanceado, né? Ele abrange 5 tipos de ataques diferentes, né? O Denial of Service, o DOS, né, amplamente conhecido, Brute Force, Malformed Packets, o Sloat e o Float. A gente também tem o dataset contém 33 atributos da camada de aplicação, que representa o comportamento das conexões MQTT. Aqui eu trouxe uma pequena amostra, né, do que você tem dentro desse dataset, né, que são o tempo de conexões de envio entre pacotes, entre outros dados. Aqui a gente tem um breve pré-processamento, né, que foi feito, né, antes da aplicação dos frameworks AutoML. Foi realizado o pré-processamento dos dados, verificamos que não havia valores ausentes ou inconsistentes, o que simplificou o processo, né? Para esse trabalho, nós classificamos esse trabalho como uma tarefa de classificação binária, onde nós criamos uma coluna em que o valor 0 representa o tráfego legítimo e o 1 representa o tráfego malicioso. Então, o 1 representa quando você tem um ataque, né, estando ocorrido na rede, né? E depois a gente fez a codificação dos atributos categóricos utilizando o label encoder, né, para garantir que todos os dados estivessem em formato numérico compatível com os frameworks AutoML, né, que usam a questão de redes neurais e vários outros algoritmos já incorporados. A questão de configuração e treinamento. O dataset ele foi dividido em 70% para treino e 30% para teste, né? Onde essa divisão já é disponibilizada pelo criador do dataset, né, por Vacari. Logo, foram avaliados 4 frameworks AutoML amplamente reconhecidos, que são o H2O AutoML, o Tpot, o Gamma e o AutoGullon. Cada framework foi executado 5 vezes, né, com um limite de 300 segundos por execução. Essa decisão de repetir o processo 5 vezes foi com o intuito de reduzir o impacto da aleatoriedade presente em algoritmos estocásticos incorporados nos modelos AutoML, né? Como o de otimização genética, os ensembles, né? O objetivo foi avaliar a estabilidade e a consistência dos modelos, né? Para que você não tenha um resultado incoerente, né? Que não seja verdadeiro, porque talvez você tenha executado uma vez e tenha tido sorte de ter um bom resultado, né? Logo, com isso, nós calculamos a média e o desvio padrão das métricas de acurácia, precisão recall e F1 score. Os resultados, referente aos resultados e a resposta também para a primeira pergunta de pesquisa, né, que é a comparação entre os frameworks, né. Logo, nós temos resultados médios de 5 execuções, né, que mostraram que o H2O AutoML apresentou o melhor desempenho, alcançando 99,99% de acurácia e um F1 score de 0,99. O Tpot ficou em segundo lugar com 98,78, seguido pelo Gamma com 94,11. E o AutoGullon com 80,10%. Logo, o H2O se destacou principalmente por utilizar os ensemble stake, né, combinando diversos algoritmos como o XBoost e redes neurais de forma automática, né? Além disso, o desvio padrão nós podemos observar que ele teve um desvio padrão muito baixo, né, o que confirma a estabilidade do modelo. Aí nós temos a segunda pergunta de pesquisa, né, que logo a automação proporcionada pelos frameworks, a AutoML reduziu significativamente a necessidade de intervenção de um especialista, né? E as etapas como seleção de algoritmos, extração de atributos e ajuste de hiperparâmetros foram totalmente automatizadas. O AutoML H2O foi o que mais estável entre todos, né? Apresentando uma baixa variabilidade entre as execuções e apresentando resultados consistentes, né? O que isso mostra que o AutoML pode gerar modelos confiáveis e precisos e reprodutíveis, mesmo sem os ajustes manuais complexos que você faria numa abordagem tradicional, né? Aqui a gente tem uma comparação com a literatura, né, onde a gente pegou o resultado do nosso estudo e comparamos com alguns estudos já disponíveis na literatura, né, que também usaram o dataset MQTT7 como base, né, como trabalho de Tushine em 2005 e Hanif em 2024. Logo, observa-se que nossos resultados foram superiores em todas as métricas, enquanto os métodos tradicionais, como Random Forest, Decision Tree, XBoost, obteram acurácia entre 90% e 96%, e nosso modelo AutoML H2O atingiu 99,99% de acurácia, com apenas 300 segundos de execução. Outro ponto que se observou foi porque o trabalho de Zigda, em 2023, usando XGBoost, atingiu 95,38% de acurácia em um tempo de 0,12 segundos, né? Um tempo relativamente baixo relacionado ao nosso modelo. No entanto, a acurácia dele não foi tão satisfatória, né? O que é muito importante em sistemas de segurança, né? Agora, falando um pouco das conclusões, podemos concluir, então, que os frameworks AutoML foram eficazes e consistentes do que os modelos tradicionais da literatura. O H2O se destacou como o melhor desempenho geral, né? Os frameworks AutoML, como Tipot e Gama, também apresentaram bons resultados, mas com alta variação entre as execuções. Uma limitação do estudo é que os testes foram realizados apenas com o dataset MQTT7, né? O que restringe a generalização para outros protocolos e cenários reais. Mas, mesmo assim, os resultados mostraram que o AutoML é uma abordagem promissora para detecção autônoma e precisa de ataques em redes IoT, né? Como trabalhos futuros, nós pretendemos validar os modelos em dispositivos embarcados, né, reais, como o ESP32 ou Raspberry Pi, levando em consideração as restrições típicas desses ambientes, né, como poder de processamento e memória. Essa etapa ela será essencial para verificar o comportamento dos modelos AutoML, né, em condições reais de operação. E em agradecimentos, né, eu gostaria de agradecer ao Programa de Pós-Graduação em Engenharia Elétrica da Universidade do Estado do Amazonas, à Universidade do Estado do Amazonas e ao Laboratório de Sistemas Inteligentes, LSI. E é isso, estou disponível para responder as perguntas.
Você está ouvindo? Está me ouvindo?
Oi.
Está me ouvindo bem?
Sim.
Sim. Então, dizendo aqui, parabéns pelo trabalho e também obrigado pela apresentação do objetivo do tema. Aí, agora, passando para a sessão de perguntas, que você vai receber da plateia ali, talvez uma pergunta que queira fazer para o professor. Bom, uma pergunta que surgiu sobre o seu trabalho, que eu queria ver se nós teremos uma resposta se talvez, pensando em, você falou dentro dos trabalhos futuros, já ter pensado na implementação dentro dos sistemas reais. Qual que seria, talvez, o nível de escalabilidade ou rentabilidade que você como limitantes para poder aplicar este tipo de sistemas? también notando que dentro de la revisión de la literatura, você encontrou trabalhos que se bem compensam.
Eu não. Desculpa, eu não estou muito ouvindo muito bem, está cortando. Oi? Por favor. Eu não estou conseguindo ouvir muito bem. A pergunta é referente a aplicações reais, como é que seria feito, é isso?
Isso, qual seria a habilidade principal, comparado com outros modelos que você mencionou, que se vê tem tempos menores de execução, também tem um pouco menor de precisão na detecção dos problemas, né? Então, qual seria aí a aplicação que você acha dentro das aplicações reais?
Eu acho que eu entendi a pergunta, né, referente a como seria feita a aplicação, né? No caso, ele pode ser integrado aos gateways dos IoT ou aos brokers MQTT para detecção autônoma em ataques em tempo real, né?
Isso mesmo. Então, bom, muito obrigado pela apresentação, Joao. Te dou parabéns pelo trabalho desenvolvido. E com isso, damos finalização às apresentações referentes à sessão 9 do doutor. E, da mesma forma, convidamos a todas as pessoas para continuar com as apresentações que seguirão na sessão da tarde. Muito obrigado pela presença.
Obrigado.